the things that arises from the periodic table being arranged the way it is that we start to see trends or properties throughout the periodic table. So we're going to talk about a few of them. We're going to look at metallic character, atomic size, the effective nuclear charge, so i.e. how much positive charge from the nucleus an electron feels, ionization energy, which has to do with removing electrons, and electron affinity, which has to do with adding in electrons. All right, so when we look at the periodic table, the general trend here is that as we go across the periodic table, we get less metallic character, and as we go down the periodic table, we get more metallic character. When we look at the arrangement of the periodic table, this makes sense because the vast majority of the periodic table, it consists of metals. We've got the non-metals over there in that right-hand side of it. And so as we go from metals to non-metals, it stands to reason that we would have less metallic character. Okay? And then as we go down the periodic table, if I'm over here in this region right here, as I go down, I start off with non-metals and I get into my semi-metals or my metalloids, and I get down to metals. So we see that trend there, that we go from not very metal-like to actual metals. And so we can look, and so if I look at period 3, as I go from sodium over to chlorine, I get less and less metallic-like. Sodium is a metal, chlorine's a non-metal, so I go from this hard, somewhat dull metal. Aluminum's got a little bit more luster than sodium does, but I get over into chlorine, which is a full-on gas. Okay? Then I go from nitrogen to phosphorus to arsenic and down, and I go from something that is very much a non-metal down to a metal. Okay? So we go from our metals to our non-metals down to our metals. And so our metallic character decreases as we go across, and it increases as we go down. Okay? When I look at the size is essentially determined by how far away from the nucleus those outermost or valence electrons are. So the further away they are, the larger in size. So as I go from period 1 to period 2, I increase in energy levels. I go from energy level 1 to energy level 2. And so in period 1, we're just in energy level 1. In period 2, now we're out a little further. So it makes sense that as we go down, we get bigger. Now as we go across, we're staying in the same energy level, okay? But we're crowding more electrons into that same energy level. What we're also doing is every time we move from one element to the next, we also add in more protons. And so we get this constriction in size as we go across the periodic table because we're crowding more electrons into the same energy level, but we're also crowding more protons into the nucleus. And so we get the size getting smaller. Okay? And so as we go across, our size gets smaller. As we go down, our size gets bigger. Now, here's that same thing, but without the transition metals. So here's the thing about the transition metals. There's a lot of other things going on with the transition metals. So when we look at our trends, we're looking at the general trends that happen mostly with the main group elements. Our transition metals are going to show some exceptions to these things because of the different things that are going on with their d orbitals. And then as we get further down, messing with the f orbitals as well. All right, then we have that effective nuclear charge. We abbreviate it with a capital Z and this EFF as a subscript. So basically, when I have an electron, okay, it feels charge from that nucleus. And so how much charge it feels is the effective nuclear charge. Because what ends up happening is I have my atom, okay, and I've got my nucleus where all my positive charges. Okay, now, if I have one electron there, I've got an interaction between my nucleus and that electron, okay? Now, let's say I have another electron. I have an interaction here, but I also have an interaction there. And then let's say I draw another one, and I have another electron and another electron, okay? Well, now I'm getting an interaction here. I'm getting an interaction here. Getting an interaction here, I'm getting an interaction here, I'm getting an interaction here. I'm getting an interaction here, I'm getting an interaction here, and so on and so forth. And so what happens is, as we add in more electrons to these higher energy levels, and even into the same energy level, now we're starting to not just have interactions between our electrons and our nucleus, but we have electron interactions. And so we get shielding there, especially from core electrons. That shielding prevents the valence electrons from feeling that full force of the positive charge from the nucleus. And so as we go across the periodic table, what we start to see is a difference in that effective nuclear charge. And so as our atomic radius gets changed, we see a different change in that effective nuclear charge. So let's think about this for a second. All right. So I'm showing that we've got a higher effective nuclear charge up there at fluorine, okay, than I do at lithium. Okay. So which one's bigger, lithium or fluorine? Well, if I go here and I look at my atomic radius, all right, it should stand to reason that the larger something is, the less the effective nuclear charge is, and the smaller something is, the higher the effective nuclear charge. And that makes sense, because if I'm smaller, I'm closer to the nucleus, so I'm going to be feeling more charge. Okay, if I'm bigger, I'm further away from the nucleus, so I'm going to be feeling less charge. Okay? All right, ionization energy. This is talking about removing the outermost electron from an atom in the gaseous state. Okay, so our metals, we know, like to lose electrons for bonding. Our nonmetals like to gain electrons. So we're going to have greater ionization energy when we get over to our nonmetals than our metals. And so our ionization energy, we're going to increase as we go across the periodic table, and we're going to decrease as we go down. Okay, so the stronger electrons are held by the nucleus, the higher the ionization energy, the more energy it's going to take to pull an electron off. And so this also goes with our trend with that effective nuclear charge. So we're increasing the effective nuclear charge as we go across. We're also increasing that ionization energy. We're decreasing that effective nuclear charge as we go down. We're also decreasing that ionization energy. So as we go down, it becomes easier to pull an electron off because we're further away from the nucleus. We're not feeling that positive charge as much. Now, we do see some interesting little dips, okay? So we'll talk about these in a moment. You can see some dips there as we go, okay? So here's our general trend. As we go across, we increase. As we go down, we decrease, okay? And again, here's these little blips, all right? So it goes up and it blips down. It goes up and it blips down, and then it goes up again. So the thing with ionization energy is it also matters what kind of electron you're pulling off. So when I look at something like lithium, all right, we're just putting one electron into an s orbital. Okay, beryllium, now we're adding another electron into that s orbital. Okay, boron, now we're in p orbitals. Carbon, nitrogen, okay? And now when we go to oxygen, we're pairing up. And so we see a blip between beryllium and boron because when we get to boron, we're starting to fill the p orbitals. We see that little blip between nitrogen and oxygen because when we go from nitrogen to oxygen, nitrogen has a single electron in all three of the p orbitals. Oxygen starts to spin pair. So it's a different type of electron, so it takes a little bit different energy to pull it off. We see that same trend between magnesium and aluminum, calcium and gallium, phosphorus and sulfur, arsenic and selenium there. Okay, so the type of electron we're pulling off does affect it, but in general, that ionization energy is going to increase as we go across the periodic table. Okay, now we get what we call first ionization energy and second ionization energy. So sodium has one valence electron. If I pull that one valence electron off, now I look like one of the noble gases. So to pull off another electron is going to cause a gigantic jump in ionization energy because now I'm pulling off a core electron instead of a valence electron. what my little face covered up here is magnesium. So the first ionization energy for magnesium is 738 kilojoules per mole. The second is 1450 kilojoules per mole, and then it jumps up to 7,730. Well, magnesium has two valence electrons. So the first comes off, the second comes off. Now we've pulled off all the valence electrons, and anything else we pull off is going to be a core electron. So we see that giant jump in ionization energy. And so you can see here, all right, so anything in red, these are core electrons, and the blue, valence electrons, okay? So anytime I go from pulling off valence electrons to pulling off core electrons, I see a huge jump in that ionization energy. Those core electrons don't want to come off. Okay. Now, electron affinity, this is adding electrons in. So we know our nonmetals like to gain electrons and form anions. So our nonmetals typically have a greater electron affinity than our metals do. A lot of electron affinities are usually written as a negative number because instead of costing energy, it yields energy. Now, this isn't true across the board, all right? The electron affinity is a little bit of a weird thing. So here's our general trend. It kind of bounces around everywhere. Like ionization energy has a little bit to do with what kind of electron you're pulling off from which orbital. The same thing occurs with electron affinity. What kind of electron am I trying to add in? Which orbital is it going into? So that generally speaking, we have more electron affinity as we go from metals to nonmetals. But as you can see here, it just kind of bounces around a lot. So it's not the perfect trend, but our nonmetals typically have a greater electron affinity than our metals do. Okay. And then just as a refresher, just to remember, our valence electrons, these occupy the outermost s and p orbitals of an atom. So boron has 3 valence electrons, silicon has 4, antimony has 5. Okay. So core, valence, so again, it's easier to pull out the valence electrons. And then when we have our transition metals, our s and our p electrons are valence electrons, and then the core are the previous ones and the d electrons, which is why when transition metals ionize, we take off the s electrons and then we mess with the d electrons. Or something like selenium is past the transition metals, so it's in group 6A, it still just has 6 valence electrons, and those d electrons aren't touched at all. Okay? And so you can see we've got these valence electron configurations that look very similar as we go from period to period.